Oh, you know what time it is? It's another vlog. Yeah, woohoo! Hooray! Alright, sit back, relax. Where did we stop? God, I don't remember. Was it the Golden Dame? No, I think we already did the Golden Dame. Yeah, we already did that. Okay. And I think we already did the quantum atom. Wait. How many blogs did we do? We did 4 blogs. And that was including the prologue. Yes. Okay. Chapter 4. Slagosi. No. Let's start with the title. The quantum atom. I swear, I'm so conflicted as to whether or not I read this or not. Whether or not I read this. Give me a second. Wait a minute. I think my previous blog was on this phone. So let me just grab it. Oh, of course, only blog 2's been uploaded. Let's see. Is my blog here? Oh, goodness, I'm sorry. He's reading fluently by the age of 2 and had read the entire Bible twice by 6. Master. Level energy comes wrapped up in bite-sized chunks, resolves the problem in an it was announced that she had been awarded the Nobel Prize for Chemistry. She had become the first scientist to win 2, having already won the physics prize in 1903. It was a tremendous achievement that was overshadowed by a scandal that broke around her during the Congress. The French press had learned that she was having an affair with a married French physicist, Paul Langevin, a slender man with an elegant mustache, was a delegate at the conference, and the papers were full of stories that the pair had eloped. Einstein, who had seen no signs of a special relationship between the two. Okay, so that's chapter 2. And then I know I have done another chapter beyond that, so... Okay, we're up to chapter 4. Why am I spending so much time deciding? Okay, we're already at 3 minutes and 42 seconds. Okay, chapter 4. The quantum atom. Slagelse, Denmark, Thursday, the 1st of August, 1912. The cobbled streets of the small, picturesque town, some 50 miles southwest of Copenhagen, were decked out in flags. Yet it was not in the beautiful medieval church, but in the civic hall that Niels Bohr and Margrethe Norland were married in a 2-minute ceremony conducted by the chief of police. The mayor was away on holiday. Harold was best man, and only close family were present. Like his parents before him, Bohr did not want a religious ceremony. He had stopped believing in God as a teenager when he had confessed to his father, "I cannot understand how I could be so taken in by all this. It means nothing whatsoever to me." Had he lived, Christian Bohr would have approved when, a few months before the wedding, his son formally resigned from a Lutheran church. Originally intending to spend their honeymoon in Norway, the couple were forced to change their plans as Bohr failed to finish a paper on alpha particles in time. Instead, the newlyweds traveled to Cambridge for a 2-week stay during the month-long honeymoon. In between visits to old friends and showing Marguerite around Cambridge, Bohr completed his paper. It was a joint effort. Niels dictated, always struggling for the right word to make his meaning clear, while Marguerite corrected and improved his English. They worked so well together that for the next few years, Marguerite effectively became his secretary. Bohr disliked writing and avoided doing so whenever he could. He was able to complete his doctoral thesis only by dictating it to his mother. You mustn't help Niels so much. You must let him learn to write himself, his father had urged to no avail. When he did put pen to paper, Bohr wrote slowly and an almost indecipherable scrawl. First and foremost, recalled a colleague, he found it difficult to think and write at the same time. He needed to talk, to think aloud as he developed his ideas. He thought best while on the move, usually circling a table. Later, an assistant or anyone he could find for the task would sit with pen poised as he paced around, dictating in one language or another. Rarely satisfied with the composition of the paper or lecture, Bohr would rewrite it up to a dozen times. The end result of this excessive search for precision and clarity was often to lead the reader into a forest where it was difficult to see the wood for the trees. With the manuscript finally completed and safely packed away, Niels and Marguerite boarded the train to Manchester. On meeting his bride, Ernest and Mary Rutherford knew that the young Dane had been lucky enough to find the right woman. The marriage indeed proved to be a long and happy one that was strong enough to endure the death of 2 of their 6 sons. Rutherford was so taken with Marguerite that for once there was little talk of physics, but he made time to read Bohr's paper and promised to send it to the Philosophical Magazine with his endorsement. Relieved and happy, a few days later, the Bohrs traveled to Scotland to enjoy the remainder of their honeymoon. Returning to Copenhagen at the beginning of September, they moved into a small house in the prosperous coastal suburb of Hellerup. In a country with only one university, physics posts rarely became vacant. Just before his wedding day, Bohr had accepted a job as a teaching assistant at the Lurenstalt, the technical college. Each morning, Bohr would cycle to his new office. He would come into the yard, pushing his bicycle faster than anyone else, recalled a colleague later. He was an incessant worker and always seemed to be in a hurry. That relaxed, pipe-smoking elder statesman of physics lay in the future. Bohr also began teaching thermodynamics as a Privatdozent at the university. Like Einstein, he found preparing a lecture course arduous. Nevertheless, at least one student appreciated the effort and thanked Bohr for the clarity and conciseness with which he had arranged the difficult material and the good style with which it had been delivered. But teaching combined with his duties as an assistant left him precious little time to tackle the problems besetting Rutherford Atom. Progress was painfully slow for a young man in a hurry. He had hoped that a report written for Rutherford while still in Manchester on his nascent ideas about atomic structure, later dubbed the Rutherford Memorandum, would serve as the basis for a paper ready for publication soon after his honeymoon. It was not to be. You see, Bohr said 50 years later in one of his last interviews he gave, I'm sorry because most of that was wrong. However, he had identified the key problem, the instability of Rutherford's atom. Maxwell's theory of electromagnetism predicted that an electron circling the nucleus should continuously emit radiation. This incessant leaking of energy sends the electron spiraling into the nucleus as its orbit rapidly decays. Radiative instability was such a well-known failing that Bohr did not even mention it in his memorandum. What really concerned him was the mechanical instability that plagued Rutherford's atom. Beyond assuming that the electrons revolved around the nucleus in the manner of planets around the sun, Rutherford had said nothing about their possible arrangement. A ring of negatively charged electrons circling the nucleus was known to be unstable due to the repulsive forces the electrons exert on each other because they have the same charge. Nor could the electrons be stationary. Since opposite charges attract, the electrons would be dragged towards the positively charged core. It was a fact that Bohr recognized in the opening sentence of his memo. In such an atom, there can be no equilibrium configuration without the motion of electrons. Sorry. The problems that the young Dane had to overcome were mounting up. The electrons could not form a ring, they could not be stationary, and they could not orbit the nucleus. Lastly, with a tiny point-like nucleus at its heart, there was no way in Rutherford's model to fix the radius of an atom. Whereas others had interpreted these problems of instability as damning evidence against Rutherford's nuclear atom, for Bohr they signaled the limitations of the underlying physics that predicted its demise. His identification of radioactivity as a nuclear and not an atomic phenomenon, his pioneering work on radioelements, what Saudi later called isotopes, and on nuclear charge convinced Bohr that Rutherford's atom was indeed stable. Although it could not bear the weight of established physics, it did not suffer the predicted collapse. The question that Bohr had to answer was, why not? Since the physics of Newton and Maxwell had been impeccably applied and forecasted electrons crashing into the nucleus, Bohr accepted that the question of stability must therefore be treated from a different point of view. He understood that to save Rutherford's atom would require radical change, and he turned to the quantum, discovered by reluctant Planck and championed by Einstein. The fact that in the interaction between radiation and matter, energy was absorbed and emitted in packets of varying size rather than continuously was something beyond the realm of time-honored classical physics. Even though like almost everyone else, he did not believe in Einstein's light quanta, it was clear to Bohr that the atom was in some way regulated by the quantum. But in September 1912, he had no idea how. All his life, Bohr loved to read detective stories. Like any good private eye, he looked for clues at the crime scene. The first were the predictions of instability. Certain that Rutherford's atom was stable, Bohr came up with an idea that proved crucial to his ongoing investigation, the concept of stationary states. Bohr had constructed his blackbody formula to explain the available experimental data. Only then did he attempt to derive his equation, and in the process stumbled across the quantum. Bohr adopted a similar strategy. He would begin by rebuilding Rutherford's atomic model so that the electrons did not radiate energy as they orbited the nucleus. Only later would he try to justify what he had done. Classical physics placed no restrictions on an electron's orbit inside an atom, but Bohr did. Like an architect designing a building to the strict requirements of a client, he restricted electrons to certain special orbits in which they could not continuously emit radiation and spiral into the nucleus. It was a stroke of genius. Bohr believed that certain laws of physics were just not valid in the atomic world, and so he quantized electron orbits. Just as Planck had quantized the absorption and emission of energy by his imaginary oscillators so as to derive this black-body equation, Bohr abandoned the accepted notion that an electron could orbit an atomic nucleus at any given distance. An electron, he argued, could only occupy a few select orbits, the stationary states, out of all the possible orbits allowed by classical physics. It was a condition that Bohr was perfectly entitled to impose as a theorist trying to piece together a viable working atomic model. It was a radical proposal, and for the moment all he had was an unconvincing circular argument that contradicted established physics. Electrons occupied special orbits in which they did not radiate energy. Electrons did not radiate energy because they occupied special orbits. Unless he could offer a real physical explanation for his stationary states, the permissible electron orbits, they would be dismissed as nothing more than theoretical scaffolding erected to hold up a discredited atomic structure. I hope to be able to finish the paper in a few weeks, Bohr wrote to Rutherford at the beginning of November. Reading the letter and sensing Bohr's mounting anxiety, Rutherford replied that there was no reason to feel pressed to publish in a hurry, since it was unlikely anyone else was working along the same lines. Bohr was unconvinced as the weeks passed without success. If others were not already actively engaged in trying to solve the mystery of the atom, then it was only a matter of time. Struggling to make headway, in December he asked for and was granted a few months sabbatical by Knudsen. Together with Marguerite, Bohr found a secluded cottage in the countryside as he set about searching for more atomic clues. Just before Christmas, he found one in the work of John Nicholson. At first, he feared the worst, but he soon realized that the Englishman was not the competitor he dreaded. Bohr had met Nicholson during his abortive stay at Cambridge and had not been overly impressed. Only a few years older at 31, Nicholson, who had since been appointed professor of mathematics at King's College, University of London, had also been busy building an atomic model of his own. He believed that the different elements were actually made up of various combinations of 4 primary atoms. Each of these primary atoms consisted of a nucleus surrounded by a different number of electrons that formed a rotating ring. Though, as Rutherford said, Nicholson had made an awful hash of the atom, Bohr had found a second clue. It was the physical explanation of the stationary states. the reason why electrons could occupy only certain orbits around the nucleus. An object moving in a straight line has momentum. It is nothing more than the object's mass times its velocity. An object moving in a circle possesses a property called angular momentum. An electron moving in a circular orbit has an angular momentum labeled L, that is just the mass of the electron multiplied by its velocity multiplied by the radius of its orbit, or simply L equals mvr. There are no limits in classical physics on the angular momentum of an electron or any other object moving in a circle. When Bohr read Nicholson's paper, he found his former Cambridge colleague arguing that angular momentum of a ring electrons could change only by multiples of h divided by 2 omega, where h is Planck's constant and omega pi, that's pi? Okay. And pi is the well-known numerical constant from mathematics 3.14. Nicholson showed that the angular momentum of a rotating electron ring could not be h divided by 2 pi, could only be h divided by 2 pi, or 2 times h divided by 2 pi, or 3 times h divided by 2 pi, or 4 times h divided by 2 pi, all the way up to n h divided by 2 pi, where n is an integer, a whole number. For Bohr, it was the missing clue that underpinned his stationary states. Only these orbits were permitted in which the angular momentum of the electron was an integer n multiplied by h and then divided by 2 pi. Letting n be 1, 2, 3, and so on generated the stationary states of the atom, in which an electron did not emit radiation and could therefore orbit the nucleus indefinitely. All other orbits, the non-stationary states, were forbidden. Inside an atom, angular momentum was quantized. It could only have the values L equals nh divided by 2 pi and no others. Just as a person on a ladder can only stand on its steps and nowhere in between, because electron orbits are quantized, so are the energies that an electron can possess inside an atom. For hydrogen, Bohr was able to use classical physics to calculate its single electron's energy in each orbit. The set of allowed orbits and their associated electron energies are the quantum states of the atoms. Its energy level is E sub n. The bottom rung of this atomic energy ladder is n equals 1, where the electron is in the first orbit, the lowest energy quantum state. Bohr's model predicted that the lowest energy level, called E1, called the ground state, for the hydrogen atom would be negative 13.6 electrovolts, where an electron volt, or eV, is the unit of measurement adopted for energy on the atomic scale, and the minus sign indicates that the electron is bound to the nucleus. If the electron occupies any other orbit but n equals 1, then the atom is said to be in an excited state. There you call the principal quantum number. N is always an integer, a whole number, which designates the series of stationary states that an electron can occupy, and the corresponding set of energy levels, E sub n, of the atom. Bohr calculated the values of the energy levels of the hydrogen atom and found the energy of each level was equal to the energy of the ground state divided by n squared. E sub 1 divided by n squared electron volts. Thus, the energy value for n equals 2, the first excited state, is negative 13.6 divided by 4 equals negative 3.40 electron volts. The radius of the first electron orbit, and 1, determines the size of the hydrogen atom. Determines the size of the hydrogen atom in the ground state. From his model, Bohr calculated it as 5.3 nanometers, where a nanometer is a billionth of a meter, in close agreement with the best experimental estimates of the day. He discovered that the radius of the other allowed orbits increased by a factor of n squared. Where n equals 1, the radius is r. When n equals 2, the radius is 4r. When n equals 3, the radius is 9r, and so on. I hope very soon to be able to send you my paper on the atoms, Bohr wrote to Rutherford on 13 January 1913. It has taken far more time than I had thought. I think, however, that I have made some progress in the latest time. He had stabilized the nuclear atom by quantizing the angular momentum of the orbiting electrons, and therefore explained why they can only occupy a certain number, the stationary states, of all possible orbits. Within days of writing to Rutherford, Bohr came across the third and final clue that allowed him to complete the construction of his quantum atomic model. Hans Hansen, a year younger and friend of Bohr's from the student days in Copenhagen, had just returned from the Danish capital after completing his studies at Göttingen. When they first met, Bohr told him about his latest ideas on atomic structure. Having conducted research in Germany in spectroscopy, the study of the absorption and emission of radiation by atoms and molecules, Hansen asked Bohr if his work shed any light on the production of spectral lines. It had long been known that the appearance of a naked flame changed color depending upon which metal was being vaporized: bright yellow with sodium, deep red with lithium, and violet with potassium. In the 19th century, it had been discovered that each element produced a unique set of spectral lines, spikes in the spectrum of light. The number, spacing, and wavelength of the spectral lines produced by the atoms of any given element are unique, a fingerprint of light that can be used to identify it. Spectra appeared far too complicated given the enormous variability of patterns displayed by the spectral lines of the different elements, for anyone to seriously believe that they could be the key to unlocking the inner workings of the atom. Oh, yeah. The beautiful array of colors on the butterfly's wing were all very interesting, Bohr said later, but nobody thought that one could get the basis of biology from the coloring of the wing of the butterfly. There was obviously a link between an atom and its spectral lines, but at the beginning of February 1913, Bohr had no inkling what it could be. Hansen suggested that he take a look at Balmer's formula for the spectral lines of hydrogen. As far as Bohr could remember, he had never heard of it. More likely he had simply forgotten it. Hansen outlined the formula of it and pointed out that no one knew why it worked. Johann Balmer was a Swiss mathematics teacher at a girls' school in Basel and a part-time lecturer at the local university. Knowing that he was interested in numerology, a colleague told Balmer about the 4 spectral lines of hydrogen after he had complained about having nothing interesting to do. Intrigued, he had set out to find a mathematical relationship between the lines where none appeared to exist. The Swedish physicist Anders Ångström had in the 1850s measured the wavelengths of the 4 lines in the red, green, blue, and violet regions of the visible spectrum of hydrogen with remarkable accuracy. Labeling them alpha, beta, gamma, and delta respectively, he found their wavelengths to be 656.210, 486.074, 434.01, and 410.12 nanometers. In June 1884, as he approached 60, Balmer found a formula that reproduced the wavelengths lambda of the 4 spectral lines. Lambda equals b times m squared divided by m squared minus n squared, in which m and n are integers and b is a constant, a number determined by experiment as 364.56 nanometers. Balmer discovered that n was fixed as 2, but m set equal to 3, 4, 5, or 6, then his formula gave an almost exact match for each of the 4 wavelengths in turn. For example, when n equals 2 and m equals 3 is plugged into the formula, it gives the wavelength of the red alpha line. However, Balmer did more than just generate the formula and spectral lines of hydrogen, later named the Balmer series in his honor. He predicted the existence of a 5th line when n was 2 but m equals 7, unaware that Ångström, whose work was published in Swedish, had already discovered and measured its wavelength. The 2 values, experimental and theoretical, were in near perfect agreement. Had Ångström lived, he died in 1874 aged 59, he would have been astounded by Balmer's use of his formula to predict the existence of other series of spectral lines for the atomic atom in the infrared and ultraviolet regions by simply setting n to 1, 3, 4, and 5, while letting m cycle through different numbers, as he had done with n set to 2, to generate the 4 original lines. For example, with n equals 3 and n equals 4 or 5 or 6 or 7, Balmer predicted that the series of lines in the infrared that were discovered in 1908. Balmer predicted the series of lines in the infrared that were discovered in 1908 by Friedrich Paschen. Each of the series forecast by Balmer were later discovered, but no one had been able to explain what lay behind the success of his formula. What physical mechanism did the formula, arrived at through a process of trial and error, symbolize? As soon as I saw Balmer's formula, Bohr said later, the whole thing was immediately clear to me. It was electrons jumping between different allowed orbits that produced the spectral lines emitted by an atom. If a hydrogen atom in the ground state, n equals 1, absorbs enough energy, then the electron jumps to a higher energy orbit, such as n equals 2. The atom is then in an unstable excited state and quickly returns to the stable ground state when the electron jumps down from n equals 2 to n equals 1. It can do so only by emitting a quantum of energy that is equivalent to the difference in energy of the two levels, 10.2 electron volts. The wavelength of the resulting spectral line can be calculated using the Planck-Einstein formula E equals hv, where v is the frequency of the emitted electromagnetic radiation. Oh, God. Okay. An electron jumping from a range of higher energy levels to the same lower energy level produced the four spectral lines of the Balmer series. The size of the quanta emitted depended only on the initial and final energy levels involved. This was why Balmer's formula generated the correct wavelengths when n was set equal to 2, but n was 3 or 5 or 5 or 6 in turn. Bohr was able to derive the other spectral series predicted by Balmer by fixing the lower energy level such that fixing the lower energy level that the electron could jump to. For example, transitions ending with the electron jumping to n equals 3 produced a Paschen series in the infrared, while those that ended at n equals 1 generated the so-called Lyman series in the ultraviolet region of the spectrum. There is, as Bohr discovered, a very strange feature associated with an electron's quantum leap. It is impossible to say where an electron actually is during a jump. The transitions during orbits, energy levels, has to occur instantaneously. Otherwise, as the atom traveled from one orbit to another, it would radiate energy continuously. In Bohr's atom, an electron could not occupy the space between orbits. As if by magic, it disappeared while in one orbit and instantly reappeared in another. I'm fully convinced that the problem of spectral lines is intimately tied to the question of the nature of the quantum. Remarkably, it was Planck, in February 1908, who wrote these words in a notebook. But in his ongoing struggle to minimize the impact of the quantum, and before the Rutherford atom, it was as far as Planck could go. Bohr embraced the idea that electromagnetic radiation was emitted and absorbed by atoms in quanta, but in 1913 he did not accept that the electromagnetic radiation itself was quantized. Even 6 years later, in 1919, few believed in Einstein's quantum of light when Planck declared in his Nobel Prize lecture that Bohr's quantum atom was the long-sought key to the entrance gate into the wonderland of spectroscopy. And that is a break, and I'm happy to have a break. And we have just 11 more pages. Nice. How many breaks though? 1, 2, just 2. Okay. Let's do just a bit of puzzle to stretch my gums. Yo, I just love it when I get to stretch my gums. Oh my god, I'm just destroying this puzzle piece. Wow. one more match and then we'll come back. Yeah, I know I'm taking a long time. I just really love puzzles. Oh, fuck it, let's come back. Alright. On 6th of March 1913, Bohr sent Rutherford the first of a trilogy of papers and asked him to send it on a philosophical magazine. At the time, and for many years to come, every junior scientist like Bohr needed someone of Rutherford's seniority to communicate a paper to a British journal to ensure swift publication. I'm very anxious to know what you may think of it all, he wrote to Rutherford. He was particularly concerned about the reaction to his mixing of the quantum of classical physics. Bohr did not have to wait long for the answer. Your ideas as to the mode of origin of spectra and hydrogen are very ingenious and seem to work out well. But the mixture of Planck's ideas with the old mechanics make it very difficult to form a physical idea of what is the basis of it all. Bohr, as others would, was having trouble picturing how the electron in the hydrogen atom jumped between energy levels. The difficulty lay in the fact that Bohr had violated a cardinal rule of classical physics. An energy moving in a circle is just an oscillating system, with one complete orbit being an oscillation and the number of orbits per second being the frequency of oscillation. And the number of orbits, an oscillating system radiates energy at the frequency of its oscillation. But since two energy levels are involved in an electron making a quantum jump, there are two frequencies of oscillation. Bohr was complaining that there was no link between these frequencies, between the old mechanics and the frequency of the radiation emitted as the electron jumps between energy levels. He also identified another more serious problem. There appears to be one grave difficulty in your hypothesis, which I have no doubt you fully realize, namely, how does an electron decide what frequency it is going to vibrate at when it passes from one stationary state to the other? It seems to me that you would have to assume that the electron knows beforehand where it was going to stop. An electron at the n equals 3 energy level can jump down to either the n equals 2 or the n equals 1 levels. In order to make the jump, the electron appears to know to which energy level it is heading so that it can emit radiation of the correct frequency. These were weaknesses of the quantum atom to which Bohr had no answer. There was another, more minor criticism that concerned Bohr far more deeply. Rutherford thought the paper really ought to be cut down, since long papers have a way of frightening readers who feel that they have not enough time to dip into them. After offering to correct Bohr's English where necessary, Rutherford added a postscript. I suppose you have no objection to my using my judgment to cut out any matter I may consider unnecessary in your paper. Please reply. When Bohr received the letter, he was horrified. Give me a second. I just saw a piece that needed to put where it was. Anyways, when Rutherford saw Bohr's letter, he was horrified. For a man who agonized over the choice of every word and went through endless drafts and revisions, the idea that someone else, even Rutherford, would make changes was appalling. 2 weeks after posting the original paper, Bohr sent a longer revised manuscript containing alterations and additions. Rutherford agreed that the changes were excellent and appear quite reasonable, but once again, he urged Bohr to cut the length. Even before he received his latest letter, he wrote to Rutherford telling him he was coming to Manchester on holiday. But when Bohr knocked on the front door, Rutherford was busy entertaining his friend Arthur Eve. He later recalled that Rutherford immediately took the slight-looking boy into his study, leaving Miss Rutherford to explain that the visitor was a young dame and her husband thought very highly indeed of his work. Through hour and hour of discussions over several long evenings during the days that followed, Bohr admitted that Rutherford showed an almost angelic patience as he tried to defend every word in his paper. An exhausted Rutherford finally gave in, and afterwards began regaling his friends and colleagues with tales of the encounter. I could see that he had weighed up every word in it, and it impressed me how determinedly he had held on to every sentence, every expression, every quotation. Everything had a definite reason, and although I first thought that many sentences could be omitted, it was clear, when he explained to me how closely knit the whole was, that it was impossible to change anything. Ironically, Bohr admitted years later that Rutherford had been right in objecting to the rather complicated presentation. Bohr's trilogy was published virtually unchanged in a philosophical magazine as On the Constitution of Atoms and Molecules. The first, dated 5th of April 1913, appeared in July. The second and third parts, published in September and November, were a presentation of ideas concerning the possible arrangements of electrons inside atoms that would preoccupy Bohr for the next decade as he used the quantum atom to explain the periodic table and the chemical properties of the elements. And that's a break. I know I'm kind of rushing through it. I think that's kind of my subconscious right now. So I try to be more deliberate in my speech for the coming sections. My goodness, we are doing splendidly regarding the puzzle. I'm just relaxing my mouth. Don't worry. I'm not like shooting someone. Imagine me with a gun. That would never happen. Whew. All right. I just saw a piece that had to be put somewhere. Okay. Bohr had built his atom using a heady cocktail of classical and quantum physics. In the process, he had violated tenets of accepted physics by proposing that electrons inside atoms can occupy only certain orbits, the stationary states. Electrons cannot radiate energy while in those orbits. An atom can be only in one of series of discrete energy states, the lowest being the ground state. Electrons can somehow jump from a stationary state of high energy to a stationary state of low energy, and the difference in energy between the two is emitted in a quantum of energy. Yet the model correctly predicted various properties of the hydrogen atom, such as its radius, and it provided a physical explanation for the production of spectral lines. The quantum atom, Rutherford said later, was a triumph of mind over matter, and until Bohr unveiled it, he believed that it would require centuries to solve the mystery of the spectral lines. A true measure of Bohr's achievement was the initial reactions to the quantum atom. It was discussed publicly for the first time on 12 September 1913 at the 83rd annual meeting of the British Association for the Advancement of Science, also known as BAAB. I tried to do a sheep sound, but I think that's too corny of a joke. Alright. Held that year in Birmingham. With Bohr in the audience, it received a muted and mixed reception. J.J. Thomson, Rutherford, Rayleigh, and Jean were all there, while the distinguished foreign contingent included Lorentz and Curie. Men over 70 should not be hasty in expressing opinions on new theories, was Rayleigh's diplomatic response when pressed for his opinion about Bohr's atom. In private, however, Bohr did not believe that nature behaved in that way and admitted that he had difficulty in accepting it as a picture of what actually takes place. Thomson objected to Bohr's quantization of the atoms as totally unnecessary. James Johns begged to differ. He pointed out in a report to the packed hall that the only justification that Bohr's model required was the very weighty one of success. In Europe, the quantum atom was greeted with disbelief. "This is all nonsense. Maxwell's equations are valid under all circumstances," said Max von Laue during one heated discussion. "An electron in a circular orbit must emit radiation." While Paul Ehrenfest confessed to Lorentz that Bohr's atom had driven me to despair, same. "If this is the way to reach the goal," he continued, "I must give up doing physics." In Göttingen, Bohr's brother Harold reported that there was great interest in his work, but that his assumptions were deemed too bold and fantastic. One early triumph for Bohr's theory clinched the support of some, including Einstein. Bohr predicted that a series of lines found in the spectrum of light from the sun that had been attributed to hydrogen actually belonged to ionized helium with one of its 2 electrons removed. This interpretation of the so-called Pickering-Fowler lines was at odds with that of its discoverers. Who was right? The issue was settled by one of Rutherford's team in Manchester after a detailed study of the spectral lines instigated at the behest of Bohr. Just in time for the Bayes meeting in Birmingham, it was found that the Dane had been correct in his assignment of the Pickering-Fowler lines to helium. Einstein heard the news during a conference in Vienna at the end of September from Bohr's friend Georg von Hevesy. "The big eyes of Einstein," reported Hevesy in a letter to Rutherford, "looked still bigger, and he told me, 'Then it is one of the greatest discoveries.'" By the time Part 2 of the trilogy was published in November 1913, another member of Rutherford's group, Henry Moseley, had confirmed the idea that the nuclear charge of an atom, its atomic number, was a unique whole number for a given element and the key parameter that decided its position within the periodic table. It was only after Bohr visited Manchester in July that year and spoke to Moseley about the atom that the young Englishman began shooting beams of electrons at different elements and examined the resulting X-ray spectra. Did I do this chapter before? Did I do this before? Oh my god, I swear. Something about it seems weirdly familiar. By then, it was known that X-rays were a form of electromagnetic radiation with wavelengths thousands of times shorter than those of visible light, and that they were produced when electrons with sufficient energy struck a given metal. Bohr believed that X-rays were emitted because one of the innermost electrons was knocked out of an atom, and an electron moved down from a higher energy level to fill the vacancy. The difference in the 2 energy levels was such that the quantum of energy emitted in the transition was an X-ray. Bohr realized that, using his atomic model, it was possible to determine the charge of the nucleus using the frequencies of the emitted X-rays. It was this intriguing fact that he had discussed with Moseley. With a prodigious capacity of work matched only by his stamina, while others slept, Moseley stayed in the laboratories working through the night. Within a couple of months, he had measured the frequencies of X-rays emitted by every element between calcium and zinc. He discovered that as the elements he bombarded got heavier, there was a corresponding increase in frequencies of the emitted X-rays. Moseley predicted the existence of missing elements with atomic numbers 42, 43, 72, and 75, on the basis that each element produced a characteristic set of X-ray spectral lines, and those adjacent to each other on the periodic table had very similar ones. All 4 were later discovered, but by then Moseley was dead. When the First World War began, he enlisted in the Royal Engineers and served as a signals officer. He died, shot through the head, in Gallipoli on 10 August 1915. His tragic death at the age of 27 robbed him of a certain Nobel Prize. Rutherford personally gave him the highest possible accolade. He hailed Moseley as a born experimenter. Bohr's correct assignment of the Pickering-Fowler lines, and Moseley's groundbreaking work on nuclear charge was beginning to win support for the quantum atom. A more significant turning point in its acceptance came in April 1914, when the young German physicists James Franck and Gustav Hertz bombarded mercury atoms with electrons and found that the electrons lost 4.9 electrovolts of energy during these collisions. Franck and Hertz believed that they had succeeded in measuring the amount of energy required to rip an electron from a mercury atom. Not having read his paper, due to the initial widespread skepticism that greeted it in Germany, it was left to Bohr to provide the correct interpretation of their data. When the electrons fired at the mercury atoms had energies of less than 4.9 electrovolts, nothing happened. But when a bombarding electron with energy above 4.9 electrovolts scored a direct hit, it lost that amount of energy, and the mercury atom emitted an ultraviolet light. Bohr pointed out that 4.9 electrovolts was the energy difference between the ground state of the mercury atom and its first excited state. It corresponded to an electron jumping between the first two energy levels in the mercury atom, and the energy difference between these levels was exactly as predicted by his atomic model. When the mercury atom returns to its ground state, as the energy jumps down to the first energy level, it emits a quantum of energy that produces an ultraviolet light of wavelength 253.7 nanometers in the mercury line spectra. The Frank-Hertz results, provided direct experimental evidence for Bohr's quantized atom and the existence of atomic energy levels. Despite initially having misinterpreted their data, Franck and Hertz were awarded the 1925 Nobel Prize in Physics. All right. And it's time for another final break. And then it's 6 straight pages, right? No. Yeah, 6 straight pages of reading. Boom. Oh, we just did massive progress on the puzzle. Shame I can't really show it to you right now. Boom. And then boom. Alright, let's finish this thing. Just as part 1 of the trilogy was published in July 1913, Bohr had finally been appointed to a lectureship at Copenhagen University. Before long, he was unhappy, as his major responsibility was to teach elementary physics to medical students. At the beginning of 1914, with his reputation on the rise, Bohr set out trying to establish a new professorship in theoretical physics for himself. It would be difficult, as theoretical physics, as a distinct discipline, was still poorly recognized as such outside Germany. Yet, In my opinion, Dr. Bohr is one of the most promising and able of the young mathematical physicists in Europe today, wrote Rutherford in the testimonial to the Department of Religious and Educational Affairs in support of Bohr and his proposal. The immense interest that his work had attracted internationally ensured that Bohr received the backing of the faculty, but once again, the university hierarchy chose to postpone any decision. It was then that the dejected Bohr received a letter from Rutherford offering an escape route. I dare say you know Darwin's tenure of readership has expired, and we are now advertising for a successor at £200, I believe that is. Rutherford wrote, preliminary inquiries show that not many men of promise are available. I should like to get a young fellow with some originality in him. Having already told the Dane that his work showed great originality and merit, Rutherford wanted Bohr without explicitly saying so. In September 1914, having been granted a year's leave of absence, as any decision on the professorship he wanted was unlikely before then, Niels and Margrethe Bohr arrived in Manchester to a warm welcome. At their safe arrival after a stormy voyage around Scotland. The First World War had begun, and much had changed. The wave of patriotism that swept the country had virtually emptied the laboratories as those eligible to fight signed up. The hope that the war would be sharp receded by the day as the Germans smashed through Belgium and into France. Men who had only recently been colleagues were now fighting on opposite sides. Marsden was soon on the Western Front. Geiger and Hevesy had joined the armies of the Central Powers. Rutherford was not in Manchester when Bohr arrived. He had left in June to attend the annual meeting of the British Association for the Advancement of Science, or the being held that year in Melbourne, Australia. Recently knighted, he visited his family in New Zealand before traveling to America and Canada as planned. Once back in Manchester, Rutherford devoted much of his time to anti-submarine warfare. Since Denmark was neutral, Bohr was not allowed to take part in any war-related activities. He concentrated largely on teaching, and what research was possible was impeded by the lack of journals and the censorship of letters from and to Europe. Just put another piece there. Okay. Originally planning to spend just a year in Manchester, Bohr was still there when in May 1916 he was formally appointed to the newly created post of Professor of Theoretical Physics in Copenhagen. The growing recognition of his work had secured the post, but despite its successes there were problems that the quantum atom could not solve. The answers it gave for atoms with more than one electron failed to tally with experiments. It could not even account for helium with just 2 electrons. Worse, Bohr's atomic model predicted spectral lines that could not be found, in spite of the introduction of ad hoc selection rules to explain why some lines were observed and others were not. All these central atoms of Bohr electron were accepted by the end of 1914. The existence of discrete energy levels, the quantization of angular momentum of the orbiting electrons, and the origin of spectral lines. However, if there existed a single spectral line that could not be explained, even with the imposition of some new rule, then the quantum atom was in trouble. Improved equipment in 1892, improved equipment appeared to show that the red alpha and blue gamma Balmer lines of the hydrogen spectrum were not single lines at all, but were each split in 2. For more than 20 years, it remained an open question whether the lines were true doublets or not. Bohr thought not. It was at the beginning of 1915 that he changed his mind as new experiments revealed that the red, blue, and violet lines were all doublet. Using his atomic model, Bohr could not explain this fine structure, as the splitting of the lines was called. As he settled into his new role as a professor in Copenhagen, Bohr found a batch of papers waiting for him from a German who had solved the problem by modifying his atom. Arnold Sommerfeld was a 48-year-old distinguished professor of theoretical physics at Munich University. Over the years, some of the brilliant young minds and students who would work under his watchful eye as he turned Munich into a thriving center of theoretical physics. Like Bohr, he loved skiing and would invite students and colleagues to his house in the Bavarian Alps to ski and talk physics. But let me assure you that if I were in music and had the time, I would sit on your lectures in order to perfect my knowledge of mathematical physics. Einstein had written to Sommerfeld in 1908 while still in the patent office. It was some compliment coming from a man described as a lazy dog by his maths professor in Zurich. Never mind. Whatever. Okay. To simplify his model, Bohr had confined electrons to move only in circular orbits around the nucleus. Sommerfeld decided to lift this restriction, allowing electrons to move in elliptical orbits, like the planets in their journey around the sun. He knew that, mathematically speaking, circles were just a special class of ellipse, and therefore circular electron orbits were only a subset of all possible quantized elliptical orbits. The quantum number, n, in the Bohr's model specified a stationary state, a permitted circular electron orbit, and the corresponding energy level. The value of n also determined the radius of a given circular orbit. However, two numbers are required to encode the shape of an ellipse. Sommerfeld therefore introduced k, the orbital quantum number, to quantize the shape of an elliptical orbit. Of all the possible shapes of an elliptical orbit, k determined those that were allowed for a given value of n. In Sommerfeld's modified model, the principal quantum number determined the value n. The principal quantum number n determined the values that k could have. If n equals 1, then k equals 1. If n equals 2, k equals 1 and 2. When n equals 3, k equals 1, 2, and 3. For a given n, k is equal to every whole number from 1 up to and including the value of n. When n equals k, the orbit is always circular. However, if k is less than n, then the orbit is elliptical. For example, when n equals 1 and k equals 1, the orbit is circular with a radius r, called the Bohr radius. When n equals 2 and k equals 1, the orbit is elliptical. But n equals 2 and k equals 2 is a circular orbit with radius 4r. Therefore, when the hydrogen atom is in the n equals 2 quantum state, its single electron can be in either the n equals 1 or n equals 2 orbits. In the n equals 3 state, the electron can occupy any one of 3 orbits, n equals 3 and k equals 1 elliptical, n equals 3, k equals 2 elliptical, and n equals 3, k equals 3 circular. Whereas in Bohr's model, n equals 3 was just one circular orbit, in Sommerfeld's modified quantum atom there was 3 permitted orbits. These extra stationary states could explain the splitting of the spectral lines of the Balmer series. To account for the splitting of the spectral lines, Sommerfeld turned to Einstein's theory of relativity. Like a comet in orbit around the sun, as an electron in an elliptical orbit heads towards the nucleus, its speed increases. Unlike a comet, the speed of the electron is great enough for its mass to increase as predicted by relativity. This relativistic mass increase gives rise to a very small energy change. The n equals 2 states, the two orbits k equals 1 and k equals 2, have different energies because k equals 1 is elliptical and k equals 2 is circular. This minor energy difference leads to two energy levels that yield two spectral lines where only one was predicted by Bohr's model. However, the Bohr-Sommerfeld quantum atom was still unable to explain two other phenomena. In 1897, the Dutch physicist Peter Zeeman discovered that in a magnetic field, a single spectral line split into a number of separate lines or components. This was called the Zeeman effect, and once the magnetic field was switched off, the splitting disappeared. Then in 1913, the German physicist Johannes Stark found that a single spectral line splits up into several lines when atoms are placed in an electric field. Rutherford contacted Bohr as Stark published his findings. I think it is rather up to you at the present time to write something on the Zeeman and electric effects if it is possible to reconcile them with your theory. Rutherford was not the first to ask. Soon after the publication of part 1 of his theory, Bohr had received a letter of congratulation from Sommerfeld. Will you also apply your atomic model to the Zeeman effect? He asked. I want to tackle this. Bohr was unable to explain it, but Sommerfeld did. His solution was ingenious. Earlier, he had opted for elliptical orbits and thereby increased the number of possible quantized orbits that an electron could occupy when an atom was in a given energy state, such as n equals 2. Bohr and Sommerfeld had both pictured orbits, whether circular or elliptical, as lying in the plane. As he tried to account for the Zeeman effect, Sommerfeld realized that the orientation of an orbit was the vital missing component. In the magnetic field, an electron can select from more permitted orbits pointing in various directions with respect to the field. Sommerfeld introduced what he called the magnetic quantum number, m, to quantize the orientation of these orbits. For a given principal quantum number n, n can only have values that range from negative n to positive n. For if n equals 2, then m has the values negative 2, negative 1, 0, 1, and 2. Oh my god. I'm just burping and shitting and all of this. I do not believe ever to have read anything with more joy than your beautiful work, Bohr wrote to Sommerfeld in March 1916. The orientation of electron orbits, or space quantization as it became known. Yo!
给一口饭。
No! Later.
Why?
Later.
Later is how later?
10 minutes.
10 minutes?
Yes.
Okay.
Where are you going?
我去给衣服，你要录音吗？
Yeah.
When?
Now.
你还没录啊？
Yeah.
你就用这点录啊？
Yeah.
你说我是先交衣服还是你先弄这个？
10 minutes. Dumbass. The orientation of electron orbits, or space quantization as it became known. God, I'm distracted now. Was experimentally confirmed 5 years later in 1921. It made available extra energy states now labeled by the three quantum numbers n, k, and m, which an electron could occupy in the presence of an external magnetic field, leading to the Zeeman effect. Necessity being the mother of invention, Sommerfeld had been forced to introduce his two new quantum numbers k and m to explain facts revealed by experiments. Leaning heavily on the work of Sommerfeld, others explained the Stark effect as resulting from the changes in the spacing between energy levels due to the presence of an electric field. Although there were still weaknesses, such as the inability to reproduce the relative intensity of the spectral lines, the successes of the Bohr-Sommerfeld atom further enhanced Bohr's reputation and earned him an institute of his own in Copenhagen. He was on his way to becoming, as Sommerfeld called him later, the director of atomic physics, through his work and the inspiration he gave others. It was a compliment that would have pleased Bohr, who had always wanted to replicate the way in which Rutherford had run his laboratory, and the spirit he had succeeded in creating among all those who had worked there. Bohr had learned more than just physics from his mentor. He saw how Rutherford was able to galvanize a group of young physicists into producing their best. In 1917, Bohr set out to replicate what he had been fortunate enough to experience in Manchester. He approached the authorities in Copenhagen about establishing an institute for theoretical physics at the university. The institute was improved as friends raised the money necessary for buildings and land. Construction began the following year, soon after the end of the war, at a site on the edge of a beautiful park not far from the city center. Work had only begun when a letter arrived that unsettled Bohr. It was from Rutherford, who was offering him a permanent professorship in theoretical physics back in Manchester. I think the two of us could try and make physics boom, wrote Rutherford. It was tempting, but Bohr could not leave Denmark just as he was about to be given everything that he had wanted. Maybe if he had gone, Rutherford would not have left Manchester in 1919 to take over from James J.J. Thomson as the director of the Cavendish Laboratory in Cambridge. Always known as the Bohr Institute, the Universitäts Institute for Theoretische Physik was formally opened in 3rd March 1921. The Bohrs had already moved into the 7-room flat on the first floor with their growing family. Following the upheavals of war and the hardships of the years that followed in its wake, the Institute was soon the creative haven Bohr hoped it would be. It quickly became a magnet for many of the world's brightest physicists, but the most talented of all of them would remain an outsider. Fucking finally, man. This thing is like, I swear, this thing, it's hurting me. Maybe. Yeah, it might be too dramatic of a word to say, but like, yeah. Ooh, finally, another chapter done. I hope I didn't already do that one already. I still have suspicions about that shit. Alright,